We can use the process of polynomial division, or sometimes synthetic division, to factor a polynomial completely, a higher degree polynomial completely over the complex numbers. In this example, we are given that x equals I times the square root of 2 is a zero of this function. We could try synthetic division with I times the square root of 2, but synthetic division with imaginary numbers is a little bit more involved than it is with real numbers. And we will have to do synthetic division twice because we also know that the conjugate of I times the square root of 2 must be a zero of this function as well. So the zeros that we know, just based on the information we're given, are I times the square root of 2 and minus I times the square root of 2. So what I'm going to do instead of synthetic division is build up factors from these to get a larger factor that we know to be a factor of this polynomial. This factor would be x minus I times the square root of 2. And this factor here would be x plus I times the square root of 2. We have now a product of conjugates which has only two terms, first term being x squared, the last term being minus I squared times the square root of 2 squared, which is just 2. So this gives me x squared minus negative 1 times 2, just replacing my I squared by negative 1. Simplifying this whole thing gets me x squared plus 2. So this tells me that x squared plus 2 is a factor of this degree 4 polynomial. If I use polynomial division now, with my degree 4 polynomial as my dividend and x squared plus 2 as my divisor, I should get a degree 2 result from that, because I'm dividing a degree 4 by a degree 2. Right? So it's going to decrease the degree by 2. So this is going to give me a quadratic result, and once I'm down to a quadratic result, I can use the quadratic formula. I might be able to just factor it by standard techniques. There's all sorts of other things that I could try at that point. So let's go ahead and set up polynomial division with x squared plus 2 going into x to the 4 minus 4x cubed plus 5x squared minus 8x plus 6. And I'm going to start with the first term divided by the first term. X to the 4th divided by x squared gives me just x squared. And when I multiply that x squared by the whole divisor, it gets me x to the 4th plus 2x squared. I'm now going to subtract, which drops out the first terms and gets me negative 4x cubed plus 3x squared minus 8x plus 6. Next quotient term is going to be first term, again divided by first term. So negative 4x cubed divided by x squared gets me just a negative 4x. Now multiplying that negative 4x by both terms of the divisor gets me negative 4x cubed minus 8x. Again, I'm going to subtract downwards, changing this minus to a plus, changing this other minus to a plus, using a different color for both of those. Again, the first terms drop out. This 3x squared comes down. Minus 8x plus 8x, those also drop out, and this plus 6 comes down. For the last quotient term, I'm going to again take first term divided by first term, which gives me just a plus 3. And as we will see, this leaves me a remainder of 0. So I'm going to now be able to just focus on my quotient up here and how I would factor that. Since this is a very simple quotient, I'm going to be able to complete this by just straight factoring this by old techniques. I can see that this would factor as x minus 3 times x minus 1 just by the trial and error method. So I now have two factors over here, two factors over here, and I can see my leading coefficient is 1. So all I have to do for my factored form is put all of those factors together. So x minus I times the square root of 2, x plus I times the square root of 2, x minus 3, and x minus 1 is my factored form. For my zeros, I'm just going to list the zeros that go with each of these factors. I times the square root of 2, minus I times the square root of 2, 3, and 1. Setting each of these factors equal to 0 would get me the zeros that I put on the top line.